Welcome everybody. Today I would like to talk to you about how to improve software-defined storage outcomes through telemetry. My name is Lars Morowski-Bre. I've been with SUSE for over 20 years and I'm currently working as an architect for our software-defined storage solution based on Ceph. Next slide, please. First, let's talk about our agenda. I will review quickly the goals and motivation of what we want to achieve with telemetry and what telemetry means. The data collection methodology. I will also talk about the scope and limitations of kind of insights and results we can get from the telemetry data we're gathering. Quickly outline what kind of analysis I've done so far. Take a look at the pictures, which is why we are all here, and the data. And then the Q&A will take offline. Next slide. So first, why do we want to better understand how Ceph is deployed? Well, that's quite obvious. We want to improve the project and product design decisions that we make. The better we understand how Ceph and SUSE Enterprise Storage are actually used in the real world, the better we can adjust our priorities. And also we want to be able to detect anomalies and trends proactively and not just in response to support incidents. Next slide. So, and this is how we envision that our telemetry data and gathering phone home capabilities augments our support story. Support stories and cases are normally only open once an issue has escalated to human attention. So you first have to have noticed the problem. That makes it difficult for spotting trends, say a 5% performance degradation in the actual deployments based on support incidents, because 5% normally get lost in the noise and support incidents wouldn't be opened. Also the data, when we want to know how Ceph is used in the real world and we were to analyze only the data we have in support incidents obviously are biased towards unhealthy environments that have experienced some kind of fault. So these are not necessarily representative of our actual deployments in the wild. So again, our goal is we want to identify issues before they escalate to support incidents and also identify trends that are not just representative of unhealthy environments. Next slide. And this is why you should care. So why should you enable the data sharing and the telemetry functionality? This allows us to make decisions that reflect your usage. So once your systems start reflecting telemetry data, we can take all the systems that are actually deployed into account automatically. We then have a better understanding of how your deployments work, what features you are using in production, and also it allows us to better tune our test systems to represent systems that are actively deployed so we can detect those anomalies before they affect the systems and before they escalate to a support incident. So there's really a strong value proposition to enabling telemetry data sharing for a customer and user point of view. Next slide. You might also ask why we don't do surveys. In addition to the telemetry data sharing, we could also run surveys and ask you which features are enabled, right? And that is true, and we plan to continue doing that because then we better understand the use cases and your intentions. But it has also shown that surveys are not always representative. Not everybody responds to surveys. There's often minor issues in survey responses, typos, difference between terabyte versus petabyte units, all those things. And also telemetry is automated and can deliver more frequent and detailed updates than we could run surveys. We could not possibly run a survey every other week or every other month. So surveys are limited in scope, depth, and frequency. So our ultimate goal is to have both surveys and telemetry data information available to make the best possible decisions. Next slide again. And here is actually a sneak preview of the survey we ran at the end of last year. We had 404 responses and a total reported capacity from those survey responses of around 1.2 exabyte, which is, quite a significant amount of capacity. This is not, and here we already see one of the minor issues. It was not always perfectly clear whether the survey results were actually filled out correctly, because some units were varied widely and we had to filter the data manually, but we hope that this is representative. We're also asking whether the users have already enabled telemetry, and 33% of all survey respondents said they had enabled telemetry. And later on, we'll check back whether this matches the reports that we have in the telemetry dataset. And we'll also have a full analysis of the community survey and use cases coming later. Now, when we talk about 33% of these users having enabled telemetry, there's also 66%, roughly 2/3, who have not yet enabled it. And here's a breakdown of why they said they hadn't enabled it. 84 users said they weren't aware the feature existed. About 3/4 said they wanted to understand data privacy better. There's some Ceph versions in the field that haven't got support for the telemetry yet, and 33 said they're in environments where telemetry can't be enabled for connectivity reasons. Obviously, with a session like this, we plan to make everybody aware that the feature exists and also discuss the data privacy guidelines. And we'll work on the other two. Carrying on. So, next slide, please. How does Ceph gather this telemetry information? So, we only report aggregate statistics to the telemetry server. The data is anonymized. There are no host names, no IP addresses, no worldwide name from storage devices. All these things are scrubbed. It's very high level information, as you will see when we talk about the reports. Capacity deployed, features enabled, features disabled, really the things that we need to understand how Ceph is used and not understand a particular environment. The dataset is also an open dataset. It's licensed under the community data license agreement sharing version 1.0, and it's shared with the Ceph Foundation and the Ceph community. As always, the larger the dataset, the better the decisions made from it, the more representative it becomes, the more significant the findings are. It's also opt-in, so it's not enabled by default. It's very simple to enable. You just type Ceph telemetry on return on one of your cluster admin nodes, and then you can enable it. And in the next slides, we'll show some of those details. Next slide, please. Right. So the Ceph community has introduced this functionality in the Ceph Mimic release, and significant enhancements have been made in Ceph Nautilus. So Ceph Nautilus is the base of SUSE Enterprise Storage 6, and SUSE has also backported it to the Luminous release, which means we'll be releasing this as a maintenance update for SUSE Enterprise Storage 5.5. And obviously, with the upcoming release of SUSE Enterprise Storage 7 and the Octopus upstream release, there are more upcoming improvements and features. Next slide. So what is included in the telemetry dataset? For example, we have total aggregate for the cluster of capacity versus usage. So we can see what your raw capacity is and how much of that is used. We can see how many OSDs there are, how many mons are deployed, the number of nodes. Obviously, what's very important for us are the Ceph versions, kernel versions, distribution aggregates, some Cephfs performance numbers, but also some Rados block device numbers, like how many are there, it's replication enabled, features like that. And also we get some insight into what crashes have occurred in the real world. And if you are curious about what kind of data the system is sharing, you can just type Ceph telemetry show. That works even if telemetry isn't enabled yet, and which will show you the data that the cluster would send to the system. Next slide, please. And now let's talk really quickly about limitations. When we talk about statistics, we have always got to be aware of the number of limitations and constraints, and otherwise we make decisions that are either too narrow or too broad. Obviously, telemetry is currently a biased sample. Ceph only supports this in fairly recent versions. It's not enabled by default, so it's only enabled for systems and administrators that have actively interacted with their cluster. So some environments may not be represented. The environments currently need access to the internet for upload, so some air-gapped environments aren't represented, and enterprise environments are actually likely underrepresented yet, simply because they are slightly more conservative and more reluctant to enable this yet. So it's not necessarily representative one-to-one. We have to treat it with care, but we can still, take a look at trends. But the exact numbers are probably not how it actually matches up in the real world. With that, let's take a look at how we did this analysis. And basically, this was a SUSE Hack Week project, which was a lot of fun. We used the standard tools for data science, Python with the IPython and pandas libraries. Most of the time, as always, was spent on data cleanup and importing the data, because this was actually the first time we ran a large analysis of the data set and had to do quite a bit of tidying up. We unfortunately don't have time to go into this, but it was quite fascinating. With telemetry, for example, we have to deal with the fact that all the systems report telemetry at slightly different times and might even miss certain intervals. So we had to do some resampling to common intervals, extrapolate, interpolate data, right? And then when we start evaluation, find things that didn't make sense and start over. So it was a very fun week with Hack Week, digging into this data set. And now, next slide, let's take a look at what kind of trends we have. So first, we'll look at some overall trends. We'll take a look at an actual bugs that we have already found with telemetry, which is always good. Feature adoption, how we can identify most common practices, and also how this can be useful for understanding the sizing of clusters in the real world, because everybody always wants to understand how other people have built their clusters. Now, first slide is obviously how many systems are reporting telemetry information over time. So here we have resampled this to basically weekly values. So a cluster that hasn't reported for a week will be dropped. That's why it's not a real straight line. Sometimes systems miss certain reporting intervals. And we can see that there's just about 180 systems at this point when the graph was generated that are reporting telemetry information. We see a minor drop at the end. That's actually there was a minor issue we had with the telemetry server at that point that has since been resolved. Next slide. The one that's always interesting is how much capacity is actually deployed with Ceph. And here, this graph is normalized to petabytes. We can see that the total capacity of the clusters reporting is just shy of 125 petabytes, and they have around 40 petabyte actual used capacity. So actually quite a large number of systems reporting. And now when we look at the next slide, quick cross-check, also taking the survey data. If we look at the systems or users that have reported they have enabled telemetry data and then aggregate the number of capacities that they have reported, we should be seeing about twice as much in this report. And that's consistent, most broadly consistent across both capacity and the number of clusters. So it looks like some people have actually not correctly answered the question in the survey, which just shows that, the more data sources you have, the more triaging you get. And hopefully we can get some people that have said they have enabled telemetry to actually turn it on in reality. Next slide. And this is a slide why the developers are doing this. This is a slide that as developers we are most interested in, or well, the first of those slides, is understanding which of our product versions and Ceph versions are deployed in the field. So here we can see that these are the Ceph major versions. The blue ones are Ceph Luminous. That was a very brief blip when we tried the backport. Then there's some versions on 13, that's Ceph Mimic, and at this point the vast majority of all systems was deployed on Ceph Nautilus. And now let's look at the next slide, a more detailed breakdown of all the minor versions of Ceph Nautilus in the field. And this is a trend that's really interesting for us as developers, because we can see new versions coming in and old versions slowly going down over time, as you expect. As systems upgrade, new versions come in, old versions drop down. But there's also another very interesting side effect. The old versions don't shrink to zero. So here we can still see that Ceph 14.2.1 is still out there and has this like almost a baseline that's not really shrinking of systems that are not being upgraded. And for us, it's obviously very interesting to eventually understand why this is happening and why people are not upgrading faster. Another artifact that you can see here is that while this shows the number of OSDs on a certain version, you can also see that obviously as systems enable telemetry, disable telemetry, the total number fluctuates, right? So if we normalize this on the next slide, we can see here, this is slightly more representative now, that it's always the relative number of all systems reporting, but unfortunately we see exactly the same trends, right? We see some systems that are upgrading quite fast and some systems that are just, sticking around and not being upgraded. We hope that we can understand this better and also help when we show to users that systems are being upgraded, that they realize that the old versions that they have should really be upgraded as well. Now, when we talk about understanding why people upgrade or why they don't, let's take a look at the next slide. We wanted to better understand when people upgrade. That could be important, for example, understanding at which point or which day of the week we should expect support incidents to come in, how we should staff our support schedule, or even when we time a release. Should we release it towards the end of the week, the beginning of the week, beginning of the month, end of the month? And we were interested in whether we were able to deduce at which time during a week users would upgrade. For that, we had to look at the rate of change for the version strings and then see how that basically computes the rate of change for that from every day of the week to the next. And then we see the result in the next slide. And here we can see that apparently most people actually upgrade on the beginning of the week. So Mondays have a much higher change of versions relative to Sundays. And there's this other part of users that are upgrading towards the end of the week, mainly on Fridays, probably Friday nights. But Wednesdays are safe. Apparently nobody upgrades in the middle of the week, and also very few people are upgrading on Sundays. So that's interesting, but we can't really nail it down to a specific day. But still, the trends that we see Mondays versus Friday updates is still, interesting, and it's interesting to see that this data actually allows us to understand that even though we only get daily reports. Next slide, please. And now let's talk about another question that is interesting to every user and every administrator of a Ceph cluster. How many placement groups should they configure per pool? Placement groups are quite important for the even balancing of data, as you're aware. And we have a rule of thumbs of having, say, 100 PGs per object storage daemon, should be rounded to a power of 2. And the exact formula is a little bit more difficult because it varies with the data distribution between pools, pool size, replication, erasure coding, all these things. But one thing that the data set allows us to understand is which placement group, so which PG nums have been configured in the real world. As we can see on the next slide. Here's a breakdown of the top 20 PG num values configured across all pools. And there are some things that made us scratch our heads. So some of these numbers are nice. When you look at the top, so the top values are power of 2. And that's nice. That's what we expect. But then we have like 192, 100, 96, 60, 12, 24, all those numbers that are very clearly not powers of 2. And when this is not a power of 2, the data distribution becomes imbalanced. So it essentially there will be placement groups that are oversized or undersized, depending on how you look at it, compared to others. That makes it very difficult for the cluster to balance data evenly, which has implications on performance, on the total usable capacity. And we were trying to understand how exactly that happened, because this is not something that we recommended. So why was this happening? Let's take a look at the next slide. And this is a breakdown when we classify PGNum as a power of 2 or not a power of 2, right? So the dark blue is PGNum is not a power of 2, and the rest is, obviously those are the values that we want, power of 2 values. And we see that there's, the majority of environments have this configured correctly, but there's a certain number of environments where it's not configured correctly. And it's a baseline. So sometimes, obviously, when you go from one value to the other, you may go through non-power of 2 values as you transition from, say, 512 to 1024. You might go through values, but this shows that it's basically a baseline. And then we dug in and we're thinking on how to remedy this. And when we go to the next slide, the first line, actually, we had an example in our documentation that showed, well, this is how you set it. And at the point in time that said, well, this is how you set it to 100. For example, we had this explanation that said, don't you use these values, but the example in place used the numbers that we didn't want configured. So we saw a bunch of people who had apparently just cut and pasted that number instead of reading the explanation of how they should set number. So the placeholder number got actually deployed in practice. So yeah, that was not intended. So we have made the documentation more clearly. We have this now in the user interface. It will actually warn when a number of this, when such a number is configured, both on the command line and in the graphical user interface. If we detect such a state, we'll throw a warning. And what's actually more interesting, we are fully automating this with a PG autoscaler module, so administrators never have to set this value again manually, which is obviously the most beneficial solution. Take away a tunable that is hard to understand for a human and replace it with an automated algorithm that does the right thing. So that's obviously the best path because it fully removes this this option for error. And there's also a URL for a blog post on more details on this story. Now, on the next slide, we can see a hint at the other kind of information we can gather from our telemetry information. We can see how many of the users and, well, how many of the clusters that are reporting telemetry, to be precise, have adopted this new functionality. And here we can see that this feature has been reporting since about mid-December 2019. So before that, we weren't actually getting the reports. And then we can see a steady stream of systems that are turning it on. And can both turn on in fully automatic mode, that's the on setting, the brown color in the middle, or at least in one mode that says, okay, the system will warn you when you have set a number that is not optimal for your cluster. And then on the next slide, here we have a combination graph. So for the systems that have enabled the PG autoscaler, which of those have any incorrect PG num values left? And here we can see 0, because all of them are in a good place. And that's exactly what we want to see. Next slide. The other thing that we want to use telemetry information for is understanding how systems are actually used. We saw a bit of that already in the previous slides, but clearly we have more data that we want to understand. Which features are used? For example, sometimes developers introduce a new feature that is supposed to replace a previous one. But we need to understand whether we're at a point in time where we can actually deprecate an old feature without inconveniencing our existing user base. Deprecating a feature that is still widely used is generally considered a no-no. And also we can then possibly understand why those systems are holding on to an existing feature instead of upgrading as intended. This helps us, prioritize development efforts, how important the bug is. When we see a bug come in a widely used feature, we can prioritize it ahead of time, say for a feature that's only being used by, millions of our population. So let's take a look at the next slide. For example, one of the things that we introduced with SUSE Enterprise Storage 5 was a different backing store for Ceph, how it stores the data on the actual storage media. That was called BlueStore. Previously it used FileStore, which stored the data as the name implies, files on XFS, and BlueStore is Ceph-specific data structures on the storage medium. And we were curious how widely this was adopted. And here we can basically see that BlueStore very much dominates the field at this point. This is so clear that it's probably actually representative. There's just, minor holdouts of FileStore that actually shrinks a very little bit over time. And we're in a pretty good position of actually deprecating FileStore for SUSE Enterprise Storage 7 and replace it with BlueStore across the line, which allows us to focus development efforts and create a better experience for everybody. Next slide. The other question is, there are various data protection schemes in Ceph that can be used. The most fundamental one is a distinction between replication versus erasure coding. Replication just stores bitwise identical copies across multiple devices, typical 3, and erasure coding is more complicated, sort of like a RAID 6, where you can freely choose your data chunks and coding chunks and so on, and basically achieve both better efficiency and better data protection schemes. We look at this slide where we take a look at the number of pools that are configured with replicated pools versus erasure-coded pools. It looks like erasure-coded pools are not in the majority, right? It looks like they're not very widely adopted when we just count the number of pools. But now let's take a look at the next slide. And here we have taken a look at the number of clusters that have a replicated pool and the number of clusters that have erasure-coded pools. And then suddenly the picture looks quite different. This shows that about 1 in 4 clusters has an erasure-coded pool. Now they may also have a bunch of replicated pools for smaller amounts of data, but almost all larger systems have erasure-coded pools. So we can see that it's actually more widely adopted than it might look if you just compare the raw numbers of the previous stack. Next slide. Then people want to understand how erasure coding is actually configured, because erasure coding gives a lot of flexibility. There are various algorithms that can be used for those erasure code parity chunks, and here we can see that the absolute vast majority of them are using Erasure, which is a default. There's a small minority that uses Intel accelerated codes, and what's quite interesting for us to see is that even though Clay that's a new codec that was only released in mid-December, we can already see that it's already being adopted, by a few number of clusters out there. So it's already seeing some good adoption. The next slide allows us to take a look at. I'm not seeing the next slide yet. Yes, there we go. The next slide allows us to see the data protection schemes that have been chosen with Erasure code. So that's the K plus M values. K is the number of data chunks, M is the number of coding chunks, and that basically determines both the number of faults that you can tolerate, which is M, and the data efficiency, which is the ratio of the two. And here we can see that the majority is using 4+2, which is S, which gives you a resilience against two failed devices at 50% overhead. So it gives you the same level of data protection as a three-way replication effectively, but at a much lower overhead. So you go from 300% total capacity usage to 150% for essentially the same protection, which is, a big win. But we can also see that obviously some systems have chosen a wider variety of values for their use cases. We can see some extreme values. That's 10+2, for example, that gives you also protection against two failures, but only at 20% overhead. But that's pretty much on the extreme end. As a 17+3, which is, that means you have to have at least 20 nodes in your cluster for that to make sense. So this helps us better understand which values are used in the real world as well. When we go to the next slide, one thing that we also report via telemetry is the configuration options that are being set in the system. We don't know what they were set to, because in some cases this would be a breach of privacy. We don't know that you have, we don't know what you have set your password to. We just know that you have set a password, if that makes sense. So we want to know that its setting has been changed from the defaults, but we don't necessarily need to know what it has been changed to. And that's also quite useful for us to understand in the development community, because that means these are the features that we have to focus on, both on the documentation side, on the user interface side. And the first one, for example, is really quite interesting for us. It shows that many systems have enabled the balancer module, that automatically balances the data distribution in the cluster, which is obviously very useful for us, and a bunch of other details that we can deduce. Another thing that we can see here, we see how many of the systems have configured a clustered public network. So that's a minimum network configuration you have to supply to Ceph, and the number of clusters that have set a dedicated cluster network. So we can deduce from this data how many of our systems are actually running a dedicated cluster network, which helps us to understand the most common topologies of how Ceph is deployed network-wise. And that already brings us to our next slide. Let's talk about the real-world sizing. Everybody wants to know what other people are doing, how much capacity they are deploying, and it actually allows us to understand where the current sweet spot is when people vote with their feet of what kind of nodes they are building, how much capacity and disk drives they are buying. So this is currently only a snapshot. It's obviously we have only been gathering this data for around 6 months now. So it's not really sufficient yet to show hardware trends over time. So we can't really show that hard drives become cheaper or more expensive over time. We can just show you what's being deployed right now. And this is what the next table does. And I'm trying to make this quick. This is a lot of data. It's very difficult to visualize. But for example, when we look at the number of OSDs per host, so that's basically the number of disk drives that are configured on a certain host. Here we have to take into account that we don't really know. We don't report every single host and OSD, right? So a cluster reports the total number of hosts and the total number of OSDs. So here we just divide one by the other and assume it's an even distribution, which is obviously not always going to be quite true in the real world as clusters change over time. But we can see here that the median cluster has 6 OSDs per host, and the maximum cluster has 63 OSDs per node, which is a lot. But that doesn't tell the whole story. We're also breaking it down for clusters below 1 petabyte and clusters above 1 petabyte. That's just an arbitrary distinction. That's what we use for talking about small clusters. From Ceph point of view, right now everything below a petabyte is something that we think of as smallish, and everything above 1 petabyte gets into the domain of larger cluster. And here you can basically see exactly what you would expect. The median host on a larger cluster has 16 OSDs, whereas on the median node on a smaller cluster has 5, as you would expect, because more capacity means more drives. But there's another trend on the high end of the spectrum. The largest clusters are not the densest ones. The clusters below 1 petabyte are actually the ones where they have 63 OSDs on a node, instead of a more reasonable number. Because as you scale out, you don't want to pack that much capacity in. Those are not the most cost-efficient chassis if you buy hundreds of them, right? The most cost-efficient chassis have 16 or 24 drives. That's a typical building size for a large cluster. And that's also then reflected in, say, when we look at the terabytes per OSD, that's roughly speaking the disk size. The larger clusters have bigger average sizes, but lower total sizes. So the larger clusters have 12 terabyte per OSD, and the smaller clusters below 1 petabyte go up to 14 terabyte, not petabyte per disk drive. That's 5 years out. And that basically shows that when you look at the larger clusters, people buy what's most cost efficient and not what's most dense, right? So that's quite interesting as well. Next slide. And another thing, adoption of flash devices versus rotating media or hard drives. We can see that there's a fairly sizable number of OSDs that are reporting as flash that can be NVMe or SSD. In this graph, we don't make that distinction. We just group all solid-state media into one, and hard drives. So this is across the entire population. The next graph on the next slide, however, looks somewhat different. When we look at this just for clusters above 1 petabyte, we see that the relative number of flash and solid state has dropped because these are not yet the most cost-efficient media when you have a lot of data to store. So when you have large-scale archives, hard drives are still king. We expect that this is one of the trends that will continue as SSDs and NVMEs drop in cost and basically push out hard drives over time. So next slide, we're almost done. What are we planning for the future enhancement for telemetry? So one of the things that's most important for us right now, this only supports online transmission. We want to support additional transport methods for relaying telemetry information so we can get information over time from air-gapped installs, from systems that are maybe behind a mail gateway, that are behind a proxy server, so that we can get more telemetry data from more systems. Possibly tying it in SUSE terms to the SEC channels and registration, so we can use those trusted channels for sharing more telemetry information and get more representative data set. This analysis has also shown that there are some metrics that we want to share or that would be useful to answer questions that we don't currently have because it gets lost in the aggregate. So for example, like we don't know the exact number of OSDs per node because we only share the total number of OSDs per cluster. So we'd like to, get a little bit more detail. We also only currently have the total capacity of the cluster and the total usage. And we have some data per pool, but not the capacity. So we would also like to know how much data is actually in Erasure-coded pools versus how much data is in replicated pools, things like this, right? And understand which client versions are used. So obviously, once you start asking questions and trying to find answers, you only end up with more questions, so we need more data. We also want to look at more of the crash data and start data mining this for identifying trends in the crashes. We also want to start data mining for performance data, so we have a bunch of work ahead of us. What's also very interesting, that's new since I did this presentation, the automated dashboards on the Ceph site are now live as well. Here you can find the URL. If you go to that site, you will see a live telemetry dashboard showing how many clusters are currently reporting, what capacities they have, and you will have some ability to explore this live with a very limited data set, but still it's a live system, which is very useful if you're having questions about this now. And you can directly see, once you enable your system, that when you turn on telemetry, it immediately jumps up. There's one more system reporting, and the capacity shows up as well. And with that, I would like to go over to question and answers. And again, I would like to encourage you to turn telemetry sharing on, because that allows us to serve you better with Ceph and all the services we have. With that, thanks for the session today, and I hope to hear from you soon.